Okay, record, and then we are going to start to share screen. Share screen. Okay, so today we will start with a new topic. Previously, what we learned, the learning algorithm is under supervised learning, and it's regarding classification. Okay, for classification, it's regarding discrete value. Okay, and we learned the perceptron and the add line, is it? And especially for add line that we discussed, we used a new concept, and also that concept is it's very foundational. Okay, regarding the machine learning, it's called the gradient descent. If you still remember, the gradient descent is a major concept, is the cost function. The cost function. Who remembers the cost function is, so in math, is it? We write some function. So the cost function is regarding what? The parameter. Who still remember? In gradient descent. Who still remember this? The concept? What? What?
Is it W or something?
Yeah, W is called what? What is W called? We need to know this, okay. What is W called?
Not the weight, right?
Yeah, very good, very good. Okay, so it's regarding weight. Okay, we need to know this basic concepts, okay, because otherwise after we learn machine learning, we don't know what that is it? So that's the cost function. That cost function is regarding weights, is it? And basically it's what? In add line, the cost function is what? Is sum of square of arrow, is it? Sum of square of arrow. And the sum of the square of arrow is regarding what? Is regarding, and also in machine learning, so far we learned what do we use to do the training. So to train, what kind of we defined as it, we call it X and Y. What are X, Y called? The term. We need to collect data. Is it to train? We need to collect data. And in pandas, basically, that's some data set, is it? So then we have an X and Y. So what is regarding, that's math expression. So what is X, what is Y in machine learning? We need to have clear understanding of this basic concept.
So X is the features,
Yeah.
and Y is the targets.
Yeah. So this is features, is it? And this is target value, is it? Target values, is it? And we said the supervised classification training is regarding discrete values. That the target value is not a continuous value, is it? It's some categorization, class, is it? And we need to collect features, is it? Then regarding the sum of the square of arrow, so what is that? Do you still remember? It's what? If you remember, you recall, So if I draw this, so I have a lot of dots. So what do the dots represent? So here is X, is it? Here is Y. So what dots represent? We need to have this clear concept. What of those dots here represent? What are the dots? The dots represent what? Represent the training and testing data, is it? Training and testing data, is it? It's the real data you collected, is it? And in add line, is it what we said is, add line is classification, okay? And the goal is you find some line, is it? And then you can do the classification, is it? So it separates the data in two classes, is it? So this is class I, this is class 2, is it something like that? That's add line. Then what the sum of square arrow mean here? So here, this represent what? What does this hat mean? Do you still remember the Y hat? So we also have this concept Y hat. What does that Y hat means?
The prediction.
Yeah, that's a prediction, is it? So what does the arrow represent? Arrow. What is arrow?
How far the prediction is from the target.
Yeah, so it's the difference, is it, between target value and the prediction, is it? So based on the line, it is, so here it shows the difference, is it? So then what is sum of the square of arrow? That's you add all of them together, is it? Add all of the samples. So here are samples. Is it? You add all of the samples, the difference, together. Is it? That's called the sum of the square of arrow. Is it? And the cost function, what we learned in add line, is based on sum of the square of arrow. Is it? And with that, what is the goal for add line training? The training is to do what? The training's goal. Training goal. What is training goal?
To reach, to converge and to be accurate, more accurate.
So mathematically speaking, what is the goal? So regarding cost function, let's discuss regarding cost function. How do you make your prediction more accurate? What's the purpose for this cost function? What's the purpose of the cost function? Otherwise, why do we need the cost function? So what's the goal here we want to achieve in order to predict more accurately?
I think it should converge to 0 or close to 0.
So this should be minimized, is it? That's the goal, okay? So the training goal is to minimize cost function, is it? Minimize cost function and make it what? Getting close to 0, is it? Getting close to 0 mathematically, we know, is it? Yeah, how do you do it? You can take a derivative, is it? So you take a derivative, is it? Take a derivative, is it partial derivative if the weight is not a single value, is it? You take partial derivative regarding each weight, is it? And set it to 0, is it? That's pure math solution to find the weight that can minimize the cost function, is it? And in that case, you need to solve, we call it a normal equation. Normal equation. Is a normal equation. Okay, but there are a lot of issues with that. Okay, regarding large data set. Okay, so sometimes it's unsolvable maybe. Okay, so that's why we introduce the concept regarding gradient descent. Okay, so gradient descent is you're going to take a step, is it? So the basic idea for the gradient descent is you're going to take a step to try to find the optimized weight. Is it? So this is regarding weight, is it optimal? And it should be at the bottom of the bowl shape, is it? We call this in math a convex, is it? But you take a step, is it? Take step. That's a learning rate. Learning rate, is it? It's each step, is it? Getting close to the bottom of the bowl shape. Okay, so that's the idea. And why we review that is because today we will start with some new learning algorithm. This time we call it linear regression model, okay? And the linear regression model, generally speaking, regression model is not for discrete value, okay? So it's for continuous value. So it's to predict continuous value, okay, regarding X and Y. So you have the X value, you predict what the Y value is, okay. So this is not a classification. It's something like, okay, I know like today's, so we have historical data, as I suppose we have historical stock data. Stock data, is it? And then you can predict tomorrow's stock data. So so you can predict the data, is it? Based on some features, okay. So it's continuous, okay. So then in math, it's some continuous thing. So it's not discrete, it's continuous, one by one, is it? Then you know the X value. If you know the X value, then you can predict the Y value, okay. And the linear regression, then the model is you use a linear line to predict it, okay. So that's a major difference, okay, between regression model and what we already learned, the classification, okay, model. So it used to do prediction. And then let's see. And so generally speaking, the linear regression model is, so this X is a feature, is it? And what we over here, then you have some, this theta 0 and theta 1, there's some constant, is it? Constant value. Is it basically it's weights. So the same concept as add line, okay? Pretty similar here. So that's why we first reviewed key concept from add line. But here is then use this linear combination as a linear combination, then you can find a y value. This y value, we call it a hypothesis, because it's regarding x. Is it regarding x? Okay, so this is also pretty similar as the add line, but add line, then next is going to use this to predict it belongs to which class. Is it here? We just stop here. We just predict the value. Okay, we predict this value. Okay, this value. And then the cost function, then the concept is also pretty similar. Okay, so it's a difference of your hypothesis value or the predicted value, is it? So this basically is our y hat. And the difference of the target value. And then you square that. Is it? It's over all samples. Over all samples. Okay, over all samples. And then also divide by 2 times f. Okay, and generally speaking, we call this mean square of error. Mean square error. Okay. MSE. So sometimes you the SS sometimes it's pretty similar. Okay. And so this is defined as cost function, also pretty similar as line, is it? And then similar idea, is it? If you want your model very precise, is it? Then we should what? Should minimize. Also minimize cost function, is it? So here is regarding to parameters, weights, is it? Minimize the cost function, is it? Minimize cost function means what? You minimize error. You minimize error, is it? And like previously I explained also, is it? There is a pure analytic way approach. So from math, is it how do you find the minimization of this value? You take derivative. Is it? You take a derivative and make it 0. Then you can find the corresponding theta 0, theta 1. Is it? And then this hypothesis will give the minimum error. And so you will be able to find the bottom of the bowl shape of the convex. Is it? So that's pure analytic. But with huge data, is that when you have a lot of features, with the increasing number of features, that you have more features, then this theta, you also need more, is it? And then when you try to analytically solve this, it involves what? Involves inversion of matrix. So sometimes that's very hard to achieve, okay? But there is a way to get around to do approximation working pretty well as what we learned before is gradient descent algorithm, okay, gradient descent. Gradient descent is, we already know it's quite helpful, okay, regarding this. So what it does is it's repeatedly doing, is it? And so each time so we start with some random weights. Random weights, is it? Theta 0, in this case, theta 1, is it? And then you choose the learning rate. Learning rate, is it? And previously we also discussed. They shouldn't be too big. Too big will cause what problem? Overshooting. Is it? And it shouldn't be too small. Why? Because too small will means it's very slowly to converge. Is it? Converge means you reach this point because it's too slow. So it will take a lot of iterations to reach this bottom point. Is it that optimum point? Okay, so that's also not ideal. Okay, so you need to choose some good learning rate. Is it? Then we take the derivative of the cost function. Is it? Use that derivative times the learning rate, and then we can update the weight. Update the weights. Is it? Because from this diagram you can see, is it? You start with some weights. Is it? So initial weight, is it? And then you use the delta W, is it? So here is delta W, is it? How do we calculate delta W, is it? And we can use the gradient to calculate delta W, is it? And it's the opposite direction, is it, of your gradient, is it? So that's why over here it's minus, is it, times the learning rate, is it? And then you get in close, okay? So anyway, you're going to update the weights, update until you get this optimal weight point, is it? Find the optimal weight point. Okay, so this is the concept of gradient descent. And we take a derivative of that cost function, is it? And basically from math, then you can find the solution, is it? So regarding weight, so this is basically our previous W0, W1. This is W1, okay. So then it's going to be what? This is our y hat, is it? Regarding sample I. Sample I is y hat, is it? So this is calculated value. Is it calculated value? Yeah, the same thing over here, is it? And regarding the features, then you can find the W1, is it? Okay, so we already know this. So it's pretty similar, is that you can see from add line. So once we understand the add line, so basically linear regression, nothing new. It's the only difference is it's continuous value. Okay, it's not a discrete value. So later on we will also be able to see. Okay, and so over here it says repeat until converge, is it? And then you can find the optimal value. And previously I also discussed, is it? The cost function is convex function, it's bowl-shaped, is it? And it has a global minima. So that's the optimal cases, is it? And so over here, it shows, is it? Over here it shows. So this is, because our goal is to find this line. Is it? Our goal is to find this line. So this is our optimal prediction line. Is it? But you may start with something like this. Is it? All sorts of line, is it? So all of those, is it? All of those represent what? In the cost function, is it? So each of it will be regarding those contour in cost function. Is it? And our goal is to find what? Find this optimal. Okay, this is the optimal point. This optimal regarding this convex, it means what? It means that minimum, that lowest point, okay? Lowest point in the convex. Okay, in that convex function. And it matches what? When you find this, it matches this specific line. Okay, this specific line. And after you get, and of course, this is not exactly match of your points, is it your sample point, but it gives the minimum error. Is it gives the minimum summation of the errors, is it? So that's the whole point here, okay? So linear regression. So the previous one, what we discussed is linear regression with simple or with a single variable. Is it because we just have X? Is it? But a lot of cases, so that single variable means you only have single feature. But in real world, that's not the case. Is that we may have multiple features. So regarding multiple features, then you need to have multiple variables. Is it? Then the notation is you have the number of features we represent as n. Is it? So this is the features. Is it? The features, and here the J. So I means what? So the superscripts is always for the I's training sample, okay? The J means for which feature, okay? So subscript is for the feature, okay? Superscript is for training sample, okay? And then regarding multiple linear regression with multiple variables, then the hypothesis is defined like this. Is it defined like this? So basically, it's similar as the weight. So basically, this theta is our weight. Is the weight? Is it with n features? Is it? And for the theta 0. The corresponding x0 we defined always as 1, is it? And do you still remember what W0? We have another name for it. What do we call it? Who still remember that? The W0? Because x0 is not a feature, is it? Features start as x1, is it? So starting feature. So we always define x0 as 1. So it's always 1. Then what is that W0? That over here, regarding our hypothesis, the theta 0 is what? You remember we discussed the name? Who still remember that? Some special name? Starting with B. Who still remember? It's what? We call it bias. Okay, so just remember, okay, it's not weight, okay, it's a bias, okay. Okay, so that's the multiple variables, is it? And if you write in math formula, is it as vector format, then this is theta and the x, so that's in vector format, is it? Okay, so that's regarding multivariant gradient descent, not gradient, linear regression, is it? And for multiple variables, linear regression, how do we find? Because that's our goal, is it? So how do we find the optimal weights. That's similar. We use gradient descent. So the concept exactly the same. Is it exactly? So you define the cost function, is it, as the mean square of error, is it? And then we can start to do gradient descent, is it? And we simultaneous update for all of the features, is it? So that's the gradient descent concept. Okay, so we understand the concept as linear regression. And next, let's take a look example. Okay. Example, I need to get, is this linear regression? I think this is a linear regression. This is linear regression. Okay, so let's get to the example, linear regression. Why I didn't get that? So let's take a look at this example, okay? This example on our course website, I also have the notes available. It's ML linear regression, okay? And you should be able to find it, okay? And this part I took from Andrew Ng's machine learning material, okay? He is the pioneer, one of the founder, okay, we can see like something like that regarding machine learning. So the first example is about a single variable, okay, we call it union variable linear regression. So let's take a look. And we also have the data, okay, the data is pretty simple, okay, so here we, it only has, if you take a look, it has one feature and two feature. Oh, no, not two feature. I got it messed up. Okay. So it has a feature and a target value. Okay. So feature and target value. Okay. So this is the sample. Okay. The samples. Okay. So we read the CSV as we have the data. It shows us a number of rows, so nothing new here. And there's describe the general information. All total, we have 97 data. Okay, 97 data. And here it also gave us the plot of the data, what it looks like. The plot of data, if you take a look at it, so it has, so this is regarding population. So the x-axis is about population, and the y-axis is about profit. Okay, profit. So it's to, based on this, is try to do what? Try to use linear regression to predict profit. Is it based on population? That's its goal. Okay, that's its goal. So, and over here, we try to use a linear model. Linear model to predict. Is it? So here it shows, so based on all of the sample data, is it? And we do scatter plotting, is it? So this is a real sample data, okay? Plotting. And then next, let's see. Okay, then over here, for the feature, we take the first column. First column as feature. is it? And the second column as what? As target value. As a target value. So here you can see it's different from add line, is it? Add line is to do classification, is it? It's to try. So here there is no classification. So here is what you try to predict what? Predict profit. You want to know how much profit I can earn, is it based on this population, is it? So that's different, okay. Then let's see. So over here, we use sklearn. We already discussed it. And the model, first what we will do is we split the training and the testing data. Here we do what? 90% of training and 10% of testing, okay? So if you view it, looks like, so this is a whole sample. So whole sample space, is it? And then you have 90%, is it, for training, and 10%, is it, for testing. Okay, so that's why we said test size, is it? You do train and test split, okay, test split. And then you can see the train size and test size also shows us. Okay, this part is simple. And then what next we are trying to do is we are trying to use a linear regression model, okay? The linear regression model, we use sklearn, so it does provide that model. From that linear model, we import linear regression. Okay, so here you use linear regression. And the first you create an object of linear regression, is it? Okay, then next, let's see what we did here. Okay. So over here for the training and the testing data, is it? And we already collect train and testing data, is it? But we need to reshape it, okay? So that data it provides is one row n column, okay? That's not what we want. So we want to reshape it, is it? As to what? N by 1, is it? Because we only have one column of the data. And I'm not sure if you still remember this negative mean, okay? So the negative means what? Means any number, is it? It's purely based on the other, and whatever the remaining, that will go to this, is it based on the multiplication, is it? Because if you set up here as 2, then what is going to be? Then it's going to be n divided by 2, n by 2. So that's the dimension. The dimension. Okay. And if you have 3, then the dimension going n by 3 by 3. So that's what the -1 means. Okay. So once you have the model, is it linear regression model, then we can train. So when you call fit, you train with training data. Okay, the data fit need to plug in with training data. Training data. Okay, so be careful here, you use training data. And what over here is different from add line is we care about, because in math you learned, is it? It's a linear model is a plus bx, something like that, is it? So we have interceptor and we have coefficient, is it? So intercept and coefficient. We need to know exactly what this two value is it? So once you have the model trained, you will get intercept and coefficient value, is it? And once you have that, you can predict with the testing value. So for the predict, you plug in with testing value, okay? Plug in with testing data. testing data. Okay, and then how do we know how accurate our model is? Is you can call the score to find the accuracy. So the accuracy in this case is 93.5%. Okay, so that's this more. You can see it's quite simple. Is it quite pretty straightforward? And next, let's see more. Is it? And here we do the predict value with all of the testing. Is it? All of the testing. Testing, I remember it has 10 testing. Is it? 10 testing. And then you can also find their mean value. Is it? And their standard deviation. Okay, standard deviation. And then you can also count the testing and the prediction value. Is it? It's not the same. Is it? It's not the same. And you can count. Is it? And here we can find it's 10. Because over here it's very hard to let the testing. And so this is a sample target value. But this sample is from testing. Is it? And this is what? This is calculated. It's going to be very hard to be exactly the same. Is it? So because this is, generally speaking, for the linear regression, is it? Those dots are the samples. The samples. And this is your calculated value. It's very hard. Your line can directly go to a sample. Is it? Go to a sample. So that's why, generally speaking, when you're testing if those two are equal, it's normally not. So this is also different from classification. Classification, it's just if this bunch of data belongs to the top or belongs to the bottom, is it? So that's a different story. Okay. And then over here, we can also find, is it, the predicted value, is it, within the certain range, is it, with the standard deviation, is it, if it is within that range, and you can also calculate the sum, and it also gives, because this represent, okay, it meet our requirement. Even though it's not exactly the same, but if it's within this range, is it, then that's fine, because in math, is it, you learned the normal distribution, is it? Normally, if it's within one standard deviation, this is mu, is it? Then we say, oh, it's fine, is it's fine. So this means, oh, the number of its 10 examples, is it meet that qualification? Okay, so this is regarding that. And then next, let's see. We can also predict with some new value. Is it? Not the training, not the sample, okay? So this is newly collected data. That's our purpose, is it? Because both training and testing belongs to the sample space, is it? And in this case, we have 3.5 and 7, is it? And then we reshape and then we time. That's the population, is it? We have these two population. Then we are going to predict their profits. So this time you see, this is regarding continuous value. Is it continuous values? Because once you assign some x value, some x value, you will get the corresponding y value. Okay, the y value. So that's why over here we said linear regression is regarding continuous value. Okay. Okay, so that's the model. We use sklearn. And for the remaining part is just implementation. So your own version how to compute a cost function. We don't want to repeat, okay, because in add line we already discussed. It's pretty similar, okay. And how to do gradient descent. Conceptually, we already know that gradient descent, okay. And we can also visualize a cost function. So it shows like this. It's a contour. Okay, you remember. So this is 3D. Is it 3D? Because why? Because you have theta 0 and theta 1. Is it? And the third dimension here, this third dimension is regarding our cost function. Okay, cost function. So I'm not too good at drawing. So it looks like a bow. Is it? If it looks like a bow. So the dinner bowl. Is it? So what's your goal is to what? What your goal is to find the bow's bottom. Is it the bow's bottom? So it's kind of like I don't have a bow here. So it's like the bow, and it's the bottom. You see, the bottom of this bow shape is a bow shape. So, and you remember previously, we also see some diagram looks like this. You remember, is it? So this is the contour. Contour. Okay, so contour, if you remember in map, is it in map you have contour, so you project. Is it you project the 3D to 2D? Is it to 2D? So that bottom, this is the lowest point. Lowest point. Is it? Because in map, just think about in map. Is it when you do survey, your map, a lot of time you see this kind of contour. Is it? Because in the real world, the land have sea level. Is it? So how do you draw in 2D regarding the 3-dimensional? Is it? So that's how we do the contour. Is it contour? So this is maybe regarding the very top, is it? And then this is regarding the very bottom. Okay, the contour, it's projected. Okay, so anyway, so this is just some concept. And generally speaking, what's good if your the gradient descent? Okay, what's the with regarding the number of iterations? Is it? So this is the cost. Is it? So if the cost function has this kind of trend, is it? So cost function decrease regarding the number of iterations of your trainings. Is it? It's getting smaller and smaller. Is it? And then stable. Is it? We call it convergence. Is it? And then this is the best scenario. Okay, that means your training is pretty good, in a pretty good shape. Okay, versus, so this is the epoch, and this is cost function. If it's something looks like that, that's a bad model. Bad model, okay. So that's the concept. And then next, let's see. So you remember I also mentioned is it, that's our goal. Our goal is to find what? Find the line of best fit. Okay, the line of best fit. So that's the best fit line. Okay, you can have a lot of line. Each line corresponding to a different contour line. Okay. Okay, so that's the single variable linear regression. Oh, we already reached our time. So I'm going to stop recording.